Yeah. Okay, thank you. Can people hear me? Okay, great. Yeah. So I'd like to start by thanking the organizers, Mas, Ali, Valor, and Han, for having me here. I must apologize first that I couldn't attend as much talk as I would like to. I'm actually now in Santa Barbara for a workshop. So please feel free to to ask questions during the talk. It's very informal, and also if you have any questions, we can also continue discussing offline. So yeah, I'm going to talk about this recent work done with the theoretical work is done with these two brilliant collaborators. Noah Yuan is now a research scientist in Shenzhen, and Margarita Davidova is my student at MIT. And these are the three papers. And we also benefited a lot from discussing with other theorists and experimentalists, collaboration with them. So this is an outline. I will first start by a brief introduction to ordinary diodes, such as semiconductor PN junctions, and not so ordinary diodes that is made from homogeneous quantum materials. In both cases, the IV characteristic is non-reciprocal, but the effect is resistive. We're dealing with resistive diodes. And then I'll come to the main subject of this talk, which is something we already heard a lot in this workshop. And this is superconducting diodes. And again, there are two scenarios. In the first case, we deal with a homogeneous superconductor. At least theoretically, we assume that there's no complication from inhomogeneous currents. We ask, can the critical currents of a superconductor be asymmetric, can be polarity dependent? And then the second scenario, we can discuss, again, theoretically, the case of Josephson junctions under what circumstances the Josephson critical current can become direction dependent. So those are Josephson diodes. So so let me start with semiconducting diodes. As we all know, if you have a PN junction, and then there's a built-in electric field in this junction region, and this breaks the left-right symmetry. And in that case, the IV characteristic is not symmetric. So in one direction, in the forward direction, we can have a very low resistance. In the opposite direction, the resistance is very high. And obviously here, we are dealing with a dissipative transport. There is a finite resistance. Also, the effect is nonlinear, right? By definition, linear response, the resistance is always symmetric. I to leading order is proportional to V. So the magnitude of current at V and minus V to this linear order is always symmetric in magnitude. But if you go to higher orders, when we go into the nonlinear regime, then this asymmetry appears. So these kind of semiconductor diodes are widely used. They are key components of modern electronics. They can convert an AC signal into an output that has a net DC components. So this is called rectification. One can also ask question, is it possible to achieve a rectification, achieve the effect of diodes without invoking any junctions, but instead can diode effect appears in the uniform homogeneous crystals. And this actually in a different community, this is called the photogalvanic effect, right? So if we consider if there's a diode effect, it means that if we shine electromagnetic waves onto a crystal, right, this will generate then a net DC electrical current. This is what is known as the photogalvanic effect. Now, most of the study of photogalvanic effect deals with high photon energy on the order of electron volt, and in other words, dealing with the optical frequency range. And here, then we are actually dealing with the interband transitions, and you may have heard concepts such as shift current, injection current, and etc. However, so this looks very different from the diode effect in DC or very low frequency electrical transport system problems. However, already from a long time ago, physicists started considering this diode effect or photogalvanic effect at very low frequency at both DC or all the way to terahertz frequencies. And at these frequencies, they are small compared to the band gap. So there's no interband transition. There's no real interband transition. And instead, the effect is governed by intra-band process, basically by governed by the effects within the Jude peak. And one scenario that can lead to diode effect here is the presence of non-trivial scatterers. For example, if you have a triangle-shaped wedge, in this case, then scattering probability when an electron scatters away from this wedge, the scattering probability from momentum k to k prime is not equal to that from k prime to k. And you can look at this figure, imagine electrons as balls bouncing off these wedges, and you can easily see that. And it was shown that this actually is sufficient to lead to a diode effect, provided that you have these kind of non-trivial scatterers arranged in a fashion with roughly the same orientation. And of course, this looks kind of artificial. So we started asking ourselves the question, in quantum materials, with featureless impurities, for example, you take the example of graphene, and we all know that the dominant scattering is the Coulomb impurities, charged Coulomb impurities that are completely featureless. And in this case, when we ask question, is diode effect possible? Now, it turns out that in quantum materials without inversion center, then generically, the electron wave function has a non-trivial character. The electron wave packet can become chiral in the sense that there is a non-trivial self-rotation associated with electron wave packet. And for example, in the case of graphene on boron nitride, when the two sublattices of the honeycomb lattice is broken, the symmetry between the two sublattices is broken, then the electron wave packet is rotating clockwise in one valley, let's say k, and the counterclockwise in the opposite valley. So as a whole system, the ground state has no net chirality because the two valleys are equally occupied. But when you drive the system out of equilibrium by passing a current, the balance between the two valleys can be broken. And these chiral electron wave packet, when they hit a simple featureless impurity, they can scatter sideways. So this is basically the quantum version of the Magnus effect. You have a self-rotating ball, and moving against the wind, and it gets deflected sideways. So this is known as a skew scattering. So it turned out we showed in this work several years ago that the skew scattering is opposite sign in the two valleys, but also there's a trigonal warping in the two valleys that are also of opposite sign. So the net effect is that when you look at the transport in second order in the electric field, it actually induces a diode effect. So there can be a net current in response to an oscillating electric field in both the longitudinal direction and as well as in the transverse direction. And this effect was recently observed by Professor Yang's group in Singapore. And you can see that this is a second order response, observed at frequency 2 omega, and the signal is quadratic, has quadratic dependence on the input signal at frequency omega. Another contribution to this second order non-reciprocal effect is called the nonlinear Hall effect. And this is in fact, we predicted with Inti Soldman quite some time ago. And again, here we rely on the fact that the electron wave function has an intrinsic chirality in the inversion braking system. And for example, electrons at momentum k and minus k, they can carry opposite barrier curvature. Again, the whole system, when it's time reversal invariant, net barrier curvature is 0, no enormous Hall effect. But so when you pass a current, you can occupy k and minus k states differently. And that leads to a net barrier curvature that's proportional to the current. And this barrier curvature then drives an enormous velocity, which is again proportional to electric field. So the electric field is in the current, this Hall current is in the transverse direction. So then it's to the second order in the applied electric field. Okay, so again, it has the same sign when you change the direction of the electric field or the voltage. Okay, so this was observed in 2019 by Choma and Suyang Xu working at MIT. Once again, you see this effect is second order measured at frequency 2 omega and has quadratic dependence on the input current at frequency omega. And this is measured in the transverse direction. So you can think of it as a diode, but in the transverse geometry. Okay, so now one can ask the same question instead for resistive systems, for normal metals, for semiconductors. Is there some intrinsic asymmetry associated with supercurrent, dissipationless currents in the superconductor? One of the nice things about the 2D materials, the 2D superconductors, is that this maximum critical current can be measured without too much complexity, without too much effort. And for example, this is work from Vala's group quite a few years ago. And this is on monolayer tungsten ditelluride, which becomes a superconductor under electron doping. And this is the current voltage characteristics. And again, you can see that there's a critical current in the forward and the backward direction. And in this case, the VDI simply magnifies the features showing here. And you can see that it's actually perfect symmetric. For ordinary superconductors, as we all know, that the critical current has no polarity to it. However, the breakthrough came about 2 years ago from this Japan group, and they observed a superconducting diode effect, an asymmetry of the critical currents, direction dependent, and this appears when you apply a magnetic field. It appears at a relatively small magnetic field. So within a range of the currents, the current flows without resistance in one direction and only in one direction. So that's a supercurrent diode. And so I wrote this commentary article shortly after the experiments came out, and I think this is probably one of my most successful predictions that really this experiment stimulated a lot of activities in this superconductivity research, and it's actually much more than I expected. So by now, you've seen in this workshop many studies, experimental, theoretical, of these superconducting diodes in various systems, from, for example, atomically thin 2D superconductors, where the effect really come from spin instead of orbital, to Josephson diodes, and etc. So let me just, this is a very, very incomplete list. Of recent experiments, for example, from Mas Ali's group, they actually found a very intriguing diode effect in Josephson junctions at 0 external magnetic field. Earlier today, we heard talks from Nicola that measured the diode effect both in the critical current as well as through the inductance. Again, work by Dmitry Evtov, who just talked before me, and also by Professor Jia Li at the Brown University about, again, zero field diode effect in twisted bilayer and trilayer graphene. I'm going to focus a little bit more on the our theory work about diode effect in two-dimensional systems that arises from Cooper pair momentum. And this is closely related to other papers that appeared around the same time. Okay. So just to remind you that if we take a superconductor, an ordinary superconductor, the ground state has 0 Cooper pair momentum. But if you pass a current in the current carrying state, it's actually a macroscopic condensate of finite momentum Cooper pairs. Okay, and I'm going to choose the gauge. Their vector potential A is 0, and the order parameter takes now this full form. It has a spatially varying phase, and Q is a momentum. It characterizes the superconducting state. So for each given Cooper pair momentum, one can calculate the energy of the system. And for a simple system with parabolic dispersion, the total energy of the system as a function of Cooper pair momentum is simply given by the kinetic energy of Cooper pairs, which has a mass of 2m, and the total number of Cooper pairs is basically in a system with 2n electrons, the total number of Cooper pairs is n, right? So from this total energy, take the derivative of total energy with respect to the vector potential, or equivalently with respect to the Cooper momentum, it gives us the total current. And again, this is exactly what you expect for a Galilean invariant system, that the VQ, which is Q divided by 2m, is called the superfluid velocity. You can think of that as the velocity of each Cooper pair, and n is the total number of Cooper pairs, and this gives you a linear relation between current and Cooper pair momentum. Experimentally, we don't set up the momentum. Instead, we pass a current, and that current corresponds to a state, a macroscopic quantum state with a given quantum momentum Q. That's directly related to current in this way. Okay, and I want to emphasize that the current carrying state of a superconductor, we should really think of it as a metastable state with enormously long lifetime. So it really, in a sense, you can really apply the thermodynamic equilibrium consideration to a current carrying superconductor. It's very different from a current carrying normal metal. That is an intrinsic dissipative state. It's irreversible. It is accompanied by Joule heating. But in a superconductor, a current carrying state, a supercurrent carrying state, can be sort of regarded as a thermodynamic state. And it's the energy of this kind of finite Q state that determines the maximum critical current. So as we increase the Cooper pair momentum, the total energy increases. So at some point, the system prefers to be non-superconducting. The energy of the superconducting state at this Cooper momentum Q becomes so large that it's larger than the energy of the normal metal. At that point, you reach the maximum possible critical current. Okay, and that is called the Depairing current. So the critical current set by the Depairing effect. Now, in the Ginzburg-Landau theory, if we're near the superconductor normal metal transition, we can actually calculate the critical current explicitly. So this is the form of the Ginzburg-Landau free energy. The quadratic term has a constant term and a Q squared term. The constant term is controlled by the temperature. It's basically it's little t is reduced temperature, is T minus Tc, so it becomes negative below the superconducting transition temperature. That's why we get a maximum height dispersion. And the coefficient of Q squared term is called superfluid stiffness. And again, you minimize the total free energy below Tc, and then you find the magnitude of the superconducting order parameter, and the supercurrent is the derivative of free energy with respect to the vector potential, or equivalently with respect to Q, and you find that it actually is determined by the product of the square modulus of the order parameter times the Q. And so minimize this, we would like to maximize the critical current. As you can see, the superfluid velocity increases with Q. However, the order parameter decreases with Q. So there's a balance. So this maximum current is obtained at certain values of Q, and that depends on the critical reduced temperature. So one can simply work out the algebra. You find that critical current is proportional to the reduced temperature to the power of 3/2. Okay, this is within the Ginzburg-Landau regime near the superconductor metal transition. And indeed, these are the measurements from quite some time ago of the Depairing current in, for example, niobium films, and this plots is essentially the critical maximum critical current as a function of temperature. And this straight line is what you expect from the Ginzburg-Landau theory, and you see that it fits the various data very nicely from Tc all the way to maybe about 70% of Tc. Okay. And of course, in the ordinary superconductor, there's no diode effect. And in order to really break the symmetry between states at Q and minus Q, one need to break both time reversal and inversion symmetry. Okay, so this is what I want to emphasize. Unlike the ordinary diodes, in ordinary diodes, the resistive state, breaking inversion symmetry is sufficient to produce asymmetric resistance, the diode effect, ordinary diode effect. But because the superconducting state is dissipationless, a current carrying superconductor can be thought of as a thermodynamic state, and then the state at momentum Q and minus Q are related by both time reversal and inversion. So one need to break both symmetries to get a diode effect, a supercurrent diode effect, to get an asymmetry in the critical current. So one way, to break such symmetry is to one way of the symmetry breaking occurs in finite momentum superconductors. Okay, so what I mean is that so there exists, at least theoretically, there exists unconventional superconductors whose ground state in equilibrium has finite Cooper pair momentum. Okay, so this is very bizarre, but as we will see, there are several scenarios where this might occur. But I want to also emphasize that we should also keep in mind that the ground state may have finite momentum, but it necessarily has zero current. This is guaranteed by thermodynamics. Okay, and so this kind of finite momentum superconductors has long been sought after in the community, and the most famous example is the so-called FFLO state. These occurs theoretically, at least believed to exist. You take a conventional S-wave spin singlet superconductor, place it under high Zeeman field, and it turned out that it was found that the ground state spontaneously develops finite Cooper pair momentum. Okay, there's a spontaneous symmetry breaking occurs here. More recently, there's work, especially in Europe, about superconductor ferromagnetic heterostructures, and I'll just briefly mention that later. And what we have considered, along with, again, there's a huge literature about this, is two-dimensional superconductors under in-plane magnetic field, where both the spin-orbit splitting, the Rashburg, for example, Rashburg type of spin-orbit splitting, and the Zeeman effect coexists. And in this case, the theory predicts that a Cooper pair momentum is guaranteed to be non-zero, and it is proportional to the applied in-plane field. Okay, so regardless of the origin of the Cooper pair momentum, once it's there in the ground state, we can say that based on symmetry point of view, there is a preferred direction, which is the direction of the ground state Cooper pair momentum. Then one expects that the critical currents along and against the direction of Q should generally be different, and that allows for a supercurrent diodes. Okay, so symmetry allows it in such finite momentum superconductors. And this is sort of also how I got interested in this problem in the first place. There are many proposals for finite momentum superconductor, but experimental evidence is scarce, right? So one of the key questions is, how do we actually detect finite momentum superconductivity and actually diode effect, which can be measured experimentally. It can be can serve as a probe of finite momentum pairing. Okay, so how much time do I have, by the way? Supposed to be 45 minutes, is that the idea?
35 plus 10.
35 plus 10, okay. I used 25 minutes, I guess, right?
Yeah, that's about right. Yeah.
Okay, sounds good. Yeah, okay, I'll try to be on time. All right, so again, this is let me start with, let me just quickly go through these three scenarios for finite momentum superconductivity. So this is the phase diagram of the FFLO state with no spin-off coupling or negligible spin-off coupling. Then there's a first order transition from a Q equals 0 BCS state to a finite momentum state. And here the Fermi surface have a Zeeman spin splitting, and the finite Q states corresponds to pairing of spin up and spin down electrons on different Fermi surfaces. And now pairing occurs with a finite momentum. Again, I'm going to use Ginzburg-Landau theory to look for the diode effect. to study the supercurrent in the direction parallel and opposite to Q. And this phase boundary between the superconductor and normal is determined by the quadratic term vanishing, the coefficient of quadratic term vanishing. And the quadratic term is a function of covariant momentum Q, and it also depends on the magnetic field. So, so near this tricritical point, so if you go along the superconductor normal boundary, you see that the covariant momentum changes from 0 all the way up to a critical field called B star, above which it becomes non-zero. And in this transition, right on the phase boundary, it's continuous. And the behavior is entirely governed by this alpha of Q. And near the critical point, it takes this form. It's something familiar from just the Landau free energy. Think of alpha as a function of Q. When the B field is higher than B star, you develop a Mexican hat dispersion, and the minimum is now at finite Q. Right. So we take this expression and calculate the critical current using the formula shown earlier, and this is what you get. And you find that basically you find that there's an asymmetry in the critical current, and you can sort of understand it that in this finite momentum state, the ground state has covariant momentum Q naught. So notice that the at Q naught, the derivative of alpha with respect to Q is 0. That's why in the equilibrium ground state there's no critical current. But now imagine you move away from the Q naught, and then it develops a finite current, but the alpha of Q is highly skewed with respect to Q naught. That's why the critical current is asymmetric in the two directions. Moreover, if you are just above B star, right, then this Mexican hat dispersion is very shallow from Q equals 0 to Q naught, and then it rises very steeply. Okay, and this means that if you are at the superconducting ground state with momentum Q naught, it means that the critical current in the forward direction is much larger than the critical current in the backward direction. So JC minus is much smaller than JC plus. In fact, you can achieve a maximum possible diode effect, a perfect diode, when you are close to this critical point. When you are just transitioning into the finite momentum state, the diode effect actually is maximum. It reaches about 100%. You have the ratio of the JC plus and JC minus goes to 0. Now, on the other hand, one can again look at this FFL phase diagram at the 0 temperature. Okay, imagine we are 0 temperature and we are close to the edge of the FFL phase. And in that case, it's known from theoretical literature that there's an analytical expression for this superfluid, for this alpha of Q in the Ginzburg-Landau theory. And it has a non-analytic dependence as a function of Q. And here I plot it like this. And here you find again, right, this function is highly asymmetric with respect to the minimum, the left and the right. But here, interestingly, the slope is much steeper at a momentum smaller than Q naught. And in this case, it means that there's a much larger critical current in the direction opposite to Q. And we again get a maximum diode effect, but it should take an opposite sign. Okay, so all these we can obtain analytically, but then everywhere in between, we did the calculation numerically, and this is the expression for the diode efficiency, and it always takes the form of some function times which is independent of temperature times the square root of the reduced temperature. So the temperature dependence is just guaranteed by the Ginzburg-Landau theory, the general structure of the Ginzburg-Landau theory. And this function delta m is plotted here as a function of applied magnetic field. In the BCS state with 0 momentum, diode effect vanishes. And then, as I said, as you just enter the FF state, the diode effect is very large and it's positive. But then as you approach towards the very high field limit, just before the FF state dies, the diode effect becomes larger again, but it achieves the opposite sign. Okay. Theoretically, we know that FFL state should exist, but the experimental search has not given us a very definitive evidence. So there's, on the other hand, there's a recent ideas that if you take a superconductor and ferromagnet, okay, it turns out that when you take a superconductor and ferromagnet metal bilayer structure, so in this case, the superconducting order parameter and magnetization coexists, for example, within the ferromagnet, right? And in this case, because of the finite magnetization in the ferromagnet, it leads to a finite vector potential. And so essentially, it sets up some kind of a Meissner type of a screening effect, and that actually produces the finite Cooper pair momentum. So I think this is a really interesting idea, and it will be worth looking for finite momentum pairing by measuring the supercurrent diode effect in the superconductor and ferromagnet metal heterostructure. So what we have focused on in the rest of this paper that came out just about a month ago is again atomically thin superconductors with both spin orbit and Zeeman fields, and many materials, 2D materials have an intrinsic inversion asymmetric structure with Rashburg, Dresselhaus type of spin orbit splitting, and so then one can ask, what if we apply an in-plane magnetic field? And because the systems can be atomically thin, orbital effect is maximally suppressed. So we are left with Zeeman and the spin orbit field. And in this case, again, depending on the direction of the magnetic field, for example, in a Rashburg type of system, when the field is parallel to the current, there's no diode effect, but when the current is perpendicular, diode effect is expected to rise. Again, this is all based on symmetry, but now we would like to study the magnitude of this effect. So yeah, let me just very quickly say that in this system, the effect arises because the Fermi surface is shifted and deformed by the magnetic field. And I'm running out of time, so I'm not going to. So all I want to say is that at a small field, the Rashburg effect dominates. We have an intra-pocket pairing within each helical Fermi surface, and this state is adiabatic connected to the BCS state at zero field. Now, at a very high field, large compared to Rashburg spin orbit splitting, then we are essentially left with Zeeman split Fermi surface, and then the pairing is dominated by the FFLO physics. It's pairing between the two pockets, and in between there's an interesting evolution. Again, take the skipping the details. So one thing that you can show that you can see relatively straightforwardly is that when in the presence of in-plane magnetic field, right, this is a quasi-particle energy spectrum as a function of momentum, and low energy quasi-particles occur around momentum kf plus and minus kf, and these kind of the splitting comes from the Rashburg effects. But when you apply magnetic field, you see that the gap structure itself is k minus k asymmetric, and as a result, when you further apply a current, you drive the system into a finite momentum state, and as the momentum increases, the gap structure is modified, and you see that eventually at some critical current or critical Cooper pair momentum, the superconducting gap closes. But because there's already a built-in asymmetry at zero current, the superconducting gap closes at different currents, J plus and J minus. So when the superconducting gap closes, very, very roughly speaking, this gives a roughly speaking estimate of the critical currents. So because the gap closes at the different values for the forward and for the backward direction, we expect critical currents to be different. Again, this is our calculation using the Ginzburg-Landau theory, and this is the evolution of the Cooper pair momentum as a function of magnetic field. And this is the, skipping the details, this is the diode effect. Again, the diode coefficient goes as the square root of reduced temperature, and the coefficient is plotted here. This is from our numerical calculation. It's linearly proportional to the applied magnetic field at a small field, and then it reaches maximum, and then it reaches maximum at a field which is close to the FFLO field, and then it decreases again. We also did analytical calculation, and we found that the diode coefficient for a small field for weak spin orbit coupling is linearly proportional to applied field linearly proportional to the Rashba orbit strength. Okay, so I think I'll just use like 1 minute to talk about the Josephson diode effect. So again, our interest is from the point of view of finite momentum pairing. So can we set up a finite momentum pairing in the Josephson junction? And here, our idea is that you take any normal superconductor junction. When we apply a magnetic field in this geometry, there's always a Meissner screening current, and that makes the superconducting order parameter have a finite momentum on the surface of the superconductor, which then induces a pair potential in the metal. So this is a universal mechanism to set up a finite momentum order parameter within the proximatized metal, right? So at zero external field, the proximity-induced order parameter is just spatially constant. They can differ by a global phase, but within each segment, it's spatially uniform. But with a small external field, one can actually induce a finite momentum order parameter. So, so again, skipping all this, so one can then ask, what about the André bound stability spectrum? What about the current phase relation in the presence of Cooper pair momentum? So Margarita obtained beautiful results, both numerically and analytically. And this is the expression she found for short junctions in the clean limit. And this first term reduces to the familiar sine phi over 2 case when the Cooper pair momentum Q is 0. But and this comes from the bound states. But on top of that, there's an additional contribution that arises from the continuum of states above the superconducting gap. And this term is a very nice, simple expression. It's linear proportional to the Cooper momentum. And the total current is the sum of the two. Okay, it turns out that even for a short junction, when the Cooper pair momentum is present, the continuum states contribute substantially to the Josephson current. And again, the diode effect is found, and the maximum diode effect reaches about 40%. And I want to say this effect is robust against the potential barriers. If you have a non-transparent interface, these are different transparency parameters. The diode effect is suppressed, as you might expect, but it's still quite substantial, even for quite non-transparent junctions. Also, the effect is quite robust, seems to be quite robust against disorder, and these are, it's maybe reduced by maybe a factor of 2 or 3, but still quite sizable. Okay, so I think I'm running out of time, so let me just summarize here. Basically, I've presented a particular theoretical perspective of superconducting diodes that comes from finite momentum pairing. This can occur in a homogeneous superconductor, and in this case, the diode effect can be used as a way to probe finite momentum pairing. That's something that the broad superconductivity community is interested in. And also, one simple way to set up finite momentum in Josephson junctions is through the Meissner effect. So even a small magnetic field that is below the HC1 can induce a substantial Cooper pair momentum, and that leads to a universal Josephson diode effect, regardless of the material being used. Thank you.
Thank you for the talk. So I see a raised hand and also a question from the chat. So how about let's see the question from the chat. And it's a question from Mars. I have a general question. Broadly speaking, does this theory conflict with or not? For example, what Dennis brought up yesterday, like can't apply this to, for example, and a symmetric stack of niobium dicyanide layers on top of each other?
Yeah, this is an excellent question. Yeah, Dennis. Yeah. So in fact, as I said, the finite momentum state is a sufficient condition to get a diode effect, but it's not a necessary condition. So in other words, there are other scenarios where a diode effect can arise. In our actually PNAS paper with Noah, we actually did a symmetry analysis for the systems with 3-fold symmetry, C3V symmetry in the presence of an outer plane magnetic field. That's the case for the TMDs with an outer plane Zeeman field. And there, indeed, symmetry allows a diode effect. Yeah. So thank you. Yeah.
And Dennis, do you still have a question?
Yes, thank you very much for a very nice talk. I would like to ask, can you maybe shortly say what is the main difference between your approach and the Edelstein theory, which was published in 1995? Because I have feeling that there are very much similarities between them. That's my first question. And the second one is that you mentioned this FFLO phase. So, and I would like to ask, it's a FF or LO phase?
Excellent. The second question is easy. It's a FF state. It's a single Q state. And this is a state that breaks inversion, breaks time reversal. The LO state preserves time reversal symmetry. So there should not be a diode effect. And the Edelstein, there are many studies, as far as I know, on the so-called critical state. It's a state that's induced by the in-plane by Zeeman effect and by Rashba-Smilde splitting. I am not aware that there's a previous explicit calculation of the diode effect in those systems.
I will send you the reference. So
okay, we had a lot of exchange with referees, and so we cited those papers, but I'm not aware of explicit calculation like the one that we just showed. Yeah, but I was happy to take a look. Yeah.
okay. Thank you.
And Alex?
Okay, thank you for this nice talk. I just have a very general question regarding this efficiency coefficient. So
right.
What exactly is what it is telling me? I understand if I have a normal diode, I will compare the forward with the reverse current, and this will tell me how good is my diode. But here in this definition, you compare supercurrent to supercurrent, not
right.
really forward to reverse. So,
well, I mean, I will say, yeah. I mean, as you said, right, we're dealing with critical currents, we're dealing with supercurrents. So the critical current in the two directions I call JC plus and JC minus, right? So this means that in the range of current that's between the two, the current can only flow in one direction without resistance, but in the other direction, it will cause finite resistance. So in this sense, a supercurrent diode is a maximum diode effect, right? It has zero resistance in the one direction and finite in the other direction. So now, how sort of of course, this effect is only useful when JC plus and JC minus differ a lot, right? So that's why I want to consider the difference of JC plus and JC minus divided by the sum. So with this definition, a maximum supercurrent diode corresponds to this delta equal 100%. Yeah.
But why do I need to have J plus to be much larger than JC minus? I just need my supercurrent to be much larger than the resistive current.
Are you asking exactly why is it useful? So that I'm not going to give.
No, what I want to say is, if this delta is very large,
yeah.
What exactly is telling me? Because I'm not really comparing forward with reverse current, right?
Well,
so
we are comparing the critical current in the forward direction and the backward direction.
But these are supercurrents, so I'm not comparing supercurrent to resistive current, which is what I should, right?
Yeah, I'm not sure I get that. So I mean, all I can say, again, being a theorist, all I can say is that I
mean, somehow this tell me, I don't know, it's my understanding is in which window my diode will work.
Right. Yeah, exactly.
But not exactly how how much efficient is this forward compared to reverse. I don't know, something like a little bit confused with it.
Okay, I see. Okay.
Okay.
That's good. Yeah,
yeah, okay.
Thanks.
Yeah, okay. Next question, Vala.
Thanks. And thanks, Liang. That was a great talk. And I was curious about the continuum supercurrent that you were describing. Could you go there?
Continuum.
Yeah, the continuum contribution in the short junction.
Oh yeah, sounds good.
Yeah. So there.
This one.
Yes. So I guess what it's these two. These are the two terms up here. Or the first one is the continuum, and the second one is the bound state.
No,
or
the
is this,
first
the
one
second
is
one is the bound state.
Second one is the first one is from bound state. Second one is from continuum.
And so the continuum has no phase dependence.
That's correct. No, so that's why naively you may ask, is this expression actually 2-pi periodic? The answer is it doesn't look like so, but it is. Yeah, it is. Yeah. So
right,
again,
it's 2-pi periodic with an offset in the current. But okay. But so the continuum contribution does not it does not contribute any inductance, is what it looks like. Is that correct?
I need to understand better. In fact, I really like this talk Nicola gave. Yeah, I didn't think about conductance before. Kinetic conductance before. But yeah, this is actually a very interesting question. Yeah,
Okay.
I don't know the answer. Yeah.
Okay, we could talk more about it because we were looking at some continuum effects before.
Actually, I do have a question. If the Nicola is still around, I'm curious. This kinetic inductance, in the measurements, do you see it also above TC? Is there a change of conductance below and above TC?
No. This is everything fully in the superconducting regime. Even far from the fluctuation regime. As soon as we have even 1 per mil of the normal resistance, one measurement will be impossible because I will kill the Q factor. So everything what I was showing is deep in the superconducting state. And but what I can tell you that increasing the temperature, you will efficiently kill the higher harmonics well before you even reach the resistive state.
Okay, thank you.
So this is we showed also temperature dependence. So it's very, very delicate. You kill much quicker the inductance, the inductive effect than so the asymmetry in the inductance and the diode effect before the critical current. So
thank you. Yeah, thank you.
All right, thank you.
I think we are running out of the Q&A time. So Christoph, could you just type your question in the chat? We can go back later.
Okay.
I mean, if it's a quick question, can we still take it? So
There's a quick remark on the Meissner effect, Q by Meissner effect.
Yeah.
It is worth, say, looking at numbers. What is the ratio of thickness and penetration depth?
Right.
If you have a niobium film with some 30 nanometers thickness, then this is a relatively strong effect because the penetration depth is short, few 10 nanometers. In the case of the, say, our aluminum thin films, which are only 5 nanometer, the penetration depth is 40 times larger than the thickness, and then it is, I guess, very small, the effect.
Well, actually, in that case, I will say that it's the following. So the induced Cooper pair momentum Q, you can ask how is it related to the applied magnetic field. So when the thickness is large, then the Cooper pair momentum is just Q times the London, Q is basically B times the London penetration depth, right? On the other hand, if the film is thin, then it's no longer London penetration depth anymore. It's something on the order of the film thickness, right? So in other words, you're either limited by the thickness or you are limited by the London penetration depth.
Yeah. Okay. That is the same statement, right? So you reduce it by this ratio.
Yeah.
Of thickness and lambda.
Yeah, that's right. Yeah.
Yes, thanks.
I mean, my understanding is that even for relatively thin films, this orbital effect, or you can call it the Meissner orbital effect, it could be very important. Yeah, that's my impression from talking to experimentalists. Yeah.
Okay.